All right, welcome everybody. We'll let people continue to filter in as we get started, but I'll start us off with a short presentation. As always, if you have any questions, feel free to send an email to tea@nd.edu for anything regarding the summer skills sessions. Today we have PLC and kind of how that fills into the controls world with Eric Verhage, and then we'll be jumping in on Thursday to 3D printing with Dominic Civitano and Charlie Wickham. So come on out on Thursday again for that. That'll be a lot of fun hearing from them as well. I'll save Q&A for the end. So today we're going to hear from Eric. Basically, Eric graduated from Ohio State in 2019. So he's pretty close to where we're at and has some experience, finding a job in an industry that may not be themed entertainment, but finding ways to sort of build his experience outside of the industry that can be super valuable to, solving problems that do exist within the industry. With that, I'll pass it off to you, Eric. Feel free to take it away.
All right. Can you hear me all right, first off? Perfect. All right, let's see. It's getting there.
Is the screen sharing option working for you? Oh, there it goes.
Yep, good. All right. Perfect. So, how's it going, everybody? My name is Eric Verhage, and I'm going to be talking about basics of PLC. Basically, I wanted to do this skill session originally just for Ohio State's TPEG. I first pitched it to OSU TPEG, just saying, basically, I've learned some stuff over the last year. I know we had talked about PLC work in the past at our TPEGs. Would anyone be interested in kind of hearing how far I've come in the year and kind of what I've learned? And Robert jumped right away and was basically like, there's this summer skills thing we're doing. Sounds like that could fit right in there. I thought that was a perfect opportunity. So thank you very much for having me here. And I'm really glad to share some of these experiences. So a little bit about me first. I am an aerospace and electrical engineer at Calspan Corporation. So what we do is we're a transonic wind tunnel testing military aircraft mostly for force and moment and trajectory simulations. So transonic is about the regime of close to the speed of sound. So anywhere from like 0.8 to 1.2 Mach is considered transonic. So to put that into a relative perspective, that's basically our max is around 1,000 miles per hour. So just to give a sense of the speed that we kind of test at. To put that in perspective even more, the fastest wind speed ever recorded was a tornado in the 1960s that went up to about 256 miles per hour. So we're basically testing aircraft 4 times the speed of the fastest wind speed ever recorded. So something kind of cool about that is, especially for the trajectory simulation tests we run, we have a parent aircraft and then a store. So they're 2 separate bodies, and we're testing them, inches apart with wind speeds blowing up to, like I said, 1,000 miles per hour. So there's some pretty impressive controls work that goes on with that, and it's really cool to be a part of. So specifically what I do there, my role is an aeronautical test engineer. So when we have a customer program, I'm kind of in charge of coordinating the control room. So obviously running a big tunnel like that requires a lot of coordination between all the people that have to set all the different stations and parameters. So I'm kind of interfacing with the customer to get what conditions they want and in what order they want to run, and kind of going around the control room and talking with the technicians to set those conditions. When I'm not doing a customer program, I get to lead some special projects, and one of those being developing electrical and control systems, which I have a lot of fun doing, and it's also given me a lot of these experiences that you will hear about today. So real quick, this is just a screenshot of the test section. So this is looking downstream of just a general aircraft that we would test. So it's an 8-foot by 8-foot test section. So to produce the wind speeds that you need in an 8 by 8-foot test section, the wind tunnel itself is absolutely massive. I think it's 33 feet tall in the largest section. So it's always really fun to be able to actually go inside it. And you're just kind of in this massive void, and it's really thick steel, so you can't hear anything. All your phones and anything with a transmitter basically is blocked out by the steel walls, so you kind of feel like you're in another world whenever you're in there. I just think that that's a pretty cool picture to describe that. Real quick fun fact, my favorite coaster is Millennium Force at Cedar Point. I've been going to Cedar Point basically all my life, and I just can't beat that ride. A close second is Renegade at Valley Fair. Kind of an underrated roller coaster, but easily my favorite GCI wooden roller coaster. A pretty underrated wooden coaster in general. If you have not ridden it, I highly suggest. So, overview on PLCs. I feel like when anyone mentions PLCs, the first thing that jumps to your mind is ladder logic, which it makes sense because I feel like most people just think PLCs are ladder logic. Ladder logic has to do with PLCs. That is true to a degree. I like to get the big picture of it. So I'm going to be talking about both the hardware aspects and the software aspects of it, because that's especially one of the things that tripped me up when I was first learning it. So for hardware in general, PLC is an acronym. If you didn't know, it stands for Programmable Logic Controller. If you didn't know that, don't feel bad. There's a lot of professionals that I work with who are a lot older than me, who have been in the industry a lot longer than I have. When I say I'm going to go work on some PLC stuff, they're like, "What's that?" Like, I don't even know what that is. So it's probably just a good thing to know what that acronym stands for. Some instances where you would use a PLC over just a traditional hardwire. It's very good for monitoring as well as control. So there's a lot of HMI applications, and it gives really good feedback to visual indicators, and as well as it has a really good safety feedback. So the PLCs that I work with specifically are Allen Bradley brand, so that's what I know and what I'm familiar with. And they have whole cards dedicated to safety, where the only things you can plug in for I/O are safety related. They have special passwords where only the people who are in charge of programming it know the passwords and can change the safety related hardware. So whereas a normal circuit, anyone kind of walking by, if it's not protected properly, could unplug things or unwire things or to that nature. PLCs are really good for handling safety. So when you would want to use a PLC over something else is where you're doing a very repetitive task, but you want it to be consistent. So a really good example is roller coaster block systems. You want that roller coaster to ride or control the same way every time, every loop, day after day, dispatch after dispatch. So PLCs are basically what's used for block systems, and we'll get into that in a little bit. For software, the language is considered ladder logic, and the environment that you program in is not ladder logic. So if you're familiar with Arduino, I'm sure a lot of us are familiar with Arduino. The language is like a C++ variant, but the environment that you program in would be like the Arduino IDE. So just a little distinction between the language and the environment. A really short background on ladder logic. It originally evolved from relay logic as a way to kind of help familiarize older electricians who had been working with relay logic all their lives, just new switches. And instead of getting into like a scripting language where they actually had to type out code, it was a really easy visual, drag. It's basically drag and drop relay logic, and you can control a lot more complicated system. So I thought it was, when I was putting this together, I was thinking of how I wanted to break up and explain hardware to you. And really the best way I thought to do it is give you some already know. So like I mentioned earlier, I'm sure a lot of us have used or at least are familiar with Arduino boards. So I can pretty much one-for-one connect everything on this Arduino board to a PLC enclosure. So first off, this is an Arduino board. This is not a microcontroller itself. So this is the only part that's actually a microcontroller. This is the board. You can think of that like a control cabinet. This is the microcontroller. This is like the brains, basically. So this is when you say you're programming an Arduino, that is the thing you are actually programming. So that takes the code and it runs and executes the code and sends the commands out to the other components on that board. So you can think of that like the brains. Power. Arduino boards have 3 ways you can power up the board. You have the USB, which you can plug into your computer. There's a socket where you can plug in like a 5-volt stepped down battery or something. And then you can also hardwire directly into the to the inputs on the board. Next, there is the I/O. So Arduino is good in that it gives you these breakout IOs like this, but you're limited into what's on the board basically, unless you have like a breakout board or something. So you're limited to 6 digital ins and 13, or I'm sorry, 6 analog ins and then 13 digital IO basically. And lastly is communication. So when you're programming, you'll plug in a USB to your USB port, plug it into the Arduino board, and you can code from there. So those are really pretty much the only components of an Arduino board. Now, here is a PLC control cabinet. This is actually one I got to lay out earlier this year, just in January or February, I think. So if it looks confusing, it's pretty much the same thing as an Arduino board. So here is the PLC itself. Again, you can think of that like the brains. That's the microcontroller. That's the thing you're actually writing the code for. That's the thing that's doing the processing and sending out the commands. Here is your power. So I'll go into a little bit of detail here because this requires a little bit of electrical knowledge and some standards. So what you see in the top left, kind of right in this area, these are called Wago blocks. Wago is just a German brand. And this is where power is coming in. So this thick black one is coming into these orange. So orange in this case is indicating live, meaning that even if the panel is turned off, whatever is in that orange is still live. So it's basically just a visual warning of, you know, be safe, don't do anything stupid. From this orange block, it is coming up through here to the breaker, and then through the breaker back up into this gray block. So it turned from orange to gray post the breaker, basically just to show that, okay, when the breaker is flipped, that gray block is now safe. It can, you don't have power to that gray block anymore. And then you have, so this is all 120, by the way, if I didn't mention that, 120 AC. So then you're going from this gray block up here, down here, and up into the power supply. So the power supply is a 24-volt DC power supply. It's being powered by 120 AC, but then the output is going to be 24 volt. So that is what is powering your PLC. So it's taking 24 volt DC in, but it's also the power supply for your 24 volt bus. So that's where you will plug, or that's how you'll wire up sensors, and basically I/O will get its power from a bus that you can create. Here's your I/O. So something really cool that Alan Bradley does, I would assume Siemens does something similar. I've never used Siemens products. This is called a remote I/O chassis. So for some lower model PLCs that you might be familiar with, a lot of the I/O is directly connected to the PLC unit itself. So it usually just plugs into the side. Allen Bradley has these remote IOs that connect to the PLC through Ethernet. So if you have a main PLC running basically your whole facility, you can have the PLC in a central location, and then all these point IOs all over your facility tied back to your PLC with Ethernet. So we do a lot of that at my facility too. We have one big ControlLogix PLC, and then off the top of my head, I can think of like 5 remote control panels all across the facility that tie back to this PLC. So what's great about that is you can control all of those applications just by plugging in an Ethernet to one PLC basically, and all of those routines are running in subroutines to your main routine. And I just think that's a good way to handle things. So this is, like I said, it's a remote IO chassis, and then there's really cool modular IO that you plug into your chassis. So right now there are 3, these are just bases, 3 IO bases, and then you would plug cards into here. And those can range from anything to 24 volt in, out, analog in, out. You can do 120 or 220 in, out. So basically there's just a lot more flexibility with some of these more expensive PLCs. So I heard someone earlier say, you know, they like PLCs, or maybe they've heard of working with PLCs, but they're just so expensive. The high-end ones, yes, can be very expensive. This one right here is called a CompactLogix. I think I bought that for about $10,000. I think the main one we run in our tunnels is about 20,000. I didn't buy that one, but yes, they can be very expensive. But part of that is they're very reliable. They have very good documentation on all of their hardware and software. But there are some cheaper methods or cheaper alternatives, which I will talk about later. So the last component of a control cabinet is communication. This is an Ethernet and fiber optic switch, basically. So you can plug Ethernet, or there's one fiber optic input in there. But that's how you can plug your computer in and program. That's how you can plug in hardware, like if you have Ethernet encoders, which we use a lot, Ethernet enabled encoders, and that, assuming one of those ports is tied back to your PLC, is all tied into the same network, so it can all talk to your PLC. Any hardware you plug into that will tie back to your PC. So again, looking at it, it might look intimidating, but really it's just the same as an Arduino with, you know, just a lot more expensive Arduino. So this might be a pretty good reference slide. I'm not sure if we're sharing these slides after, but this is kind of a good just reference slide of what makes up like a very basic control cabinet. This is pretty much at this point suited for any application. Like this is just a blank slate. I don't have any inputs tied in. This is basically just like the foundation for a controls cabinet. So what you would do from here is you can mount this in a actual cabinet, because this is just a panel. So we laid out that back panel, and you would put it in a control cabinet. Now there's a whole bunch of different standards for cabinets, which kind of shocked me the first time I tried to buy one. There was like 30 different part numbers for a control cabinet that looked identical, but they're graded for different things like oil resistance, water resistance, pressure resistance. So it can be kind of overwhelming, but pretty much to buy equipment, you want to figure out exactly what you need, because something, if you overbuy, you can end up losing a lot of money for something you don't actually need. So when you have a cabinet like this, you can see I have one here, but you can punch out holes, and you can put interactive things on the front of that panel, which a few of you might be used to if you're a ride op. So right now that is just a light, and another example is this, which is something that I have worked quite a bit on over the last year. So basically what is sitting behind that panel right now is something almost exactly like this. There's just a lot of push buttons, LEDs, there's an emergency stop, there's visual lamps, there's a Ethernet plug, face mount. So all of that will go into these, your inputs. So that probably looks something a lot of you might be familiar with. In fact, it might look like that, which is a roller coaster control panel, specifically Top Thrill Dragster. So in other words, I did program Top Thrill Dragster is what you should all get from this. Let's see. Okay, let's move on to language. So ladder logic, like I said, is the language. It was kind of taken from relay logic. So if you're familiar with relays, this will probably look pretty familiar. Basically, all it consists of is a rung, and then rungs connecting them. So it looks like a ladder. That's how it gets the name. It's ladder logic. So it consists of inputs called contacts, and then outputs called coils. So the flow of ladder logic is every input has to be energized for the output coil to be energized. So for instance, right here, if I had a push button and I push the push button, you'll energize your input contact, which will in turn energize your output coil. So some variants of that, if you had two contacts in series, you would have to do both. You would have to energize both contacts before your coil could energize. And that's how you do a lot of monitoring. Like I was mentioning earlier, we have a whole subroutine dedicated to faults. And basically, all of the output coils in an ideal situation, all of your output coils are de-energized. If you're noticing something is not working, you can pull up your program and see which output coil is being energized, which would indicate a fault on that rung. And you can trace it back to see exactly which contact is causing that fault. So like I mentioned earlier, it's very good for debugging and monitoring safety and faults. This can also be, if you're more familiar with scripting languages like Python or MATLAB, this is the equivalent right now of like an AND statement. So if I had two of those input contacts in series, it would be the equivalent of input 1 and input 2, and then underneath it would be your output coil. Now there's you can put coils in series as well, which would be the equivalent of an OR statement. So that is used for a lot of, let's see, it's used for like redundancy checking. So if you have an open switch and then a closed switch, you can kind of put them in parallel with each other to make sure that both are being activated for your output coil. So that was the language, and here is an example of the environment. So this is the environment that I program in. This is not a program that I made. I just took this from a snapshot from a YouTube video, but it's basically just showing the layout. Specifically, this is Studio 5000 Logix Designer. It's an Allen Bradley product, and it's really easy to use, and it also has very good documentation. So if you're interested in PLC and Allen Bradley, all of their manuals for all of their hardware and software are available in PDFs for free on their websites. So it's cool to just look through sometimes to see the possibilities, even if you don't have the physical unit. I use those all the time for troubleshooting. They're very well documented and super useful. So real quick, I'll do a rundown of the environment. So this side panel is where you can add basically I/O. You can do a couple things in here. So those remote chassis, you would add those to the Ethernet section, kind of right here. You can. It's really easy. It's like a right-click, add new module, and you can initialize it basically. So you can say how many cards you have, initialize all of the cards, and basically you're good to go. So they make it pretty easy for that. Logix Designer also has a very good tags. So what that is, on some lower end PLCs, you would have to know exactly what inputs or outputs you have tied to specific inputs or outputs on your PLC. So let's say you had a proximity sensor on some input. You would have to call that by saying, you know, like PLC local unit, card 2, input 2. And you would have a really hard time remembering what that actually is. Alan Bradley in Logix Designer has something called tags, where you can basically give nicknames to all of your inputs and outputs with descriptions. It's really good for documentation. You can print out like manuals based on your code. So you can program it all, print it all out, hand it to someone, and they can review like hard copies of your code, which is also really cool. And they don't have to know what's tied exactly to what input or output because they have those tags. So for an example, we have pins on a wall we're controlling, and there's 4 pins. So if one of them faults, we need to know which one caused the fault. So we give them each a name of, you know, like top left, top right, bottom left, bottom right. So when you're looking through the faults and looking through the monitoring, you can look at the tag and say, okay, it was the, you know, the bottom left one again. I think that's about it for the side panel. The ribbon up top is where, like I mentioned earlier, you kind of drag and drop code. It's a really pretty efficient interface. That's basically where you're adding rungs and you're adding logic to those rungs. There's a button. Actually, it's not open. Oh, it's right here. So right here would be like an add a rung. So you can add as many rungs as you want. You can click on that rung in the interface, and then you can add all your logic to that rung. Top left is you can view and edit the state of your PLC. So there's a run mode, a program mode, a remote run mode. And basically that's just saying like what state your PLC is in. So what I really like about Alan Bradley, I'm not sure if other PLCs do this. Like I said, I pretty much have exclusively used Alan Bradley PLCs, but you can be in run mode and still be programming and making changes while you're running all these other applications. So that's super important, especially to me, because we are constantly running the tunnel, and I don't want to take off all of these critical applications offline to be making changes to code or to be adding new features or functions or anything. So basically, you can be writing all your code, saving all your code, and then at the very last minute, you can upload code to device. So if you have 2 minutes, if you have 2 minutes of downtime, you can in that time upload, and it'll kind of refresh the program and flash all of that to your PLC. So something, again, I'm not sure if lower end PLCs have, is this has memory. So if you lose power, you don't lose your program. Like you don't have to reflash your program onto your PLC. It restores and remembers all of your information basically. And then this is your programming environment basically. You can think of it like a command window for MATLAB or something. So it looks probably similar but better than the PowerPoint art I drew a couple slides earlier, where you've got a rung on the left, a rung on the right, and then some ladder logic. So this is essentially the same thing I drew. These are just examine open contacts. So you can think of that like a push button. So it's showing green right now because those contacts are being energized. So someone somewhere is pushing down that push button, which means everything to the right of that is happening. So this is something, obviously, it's not as straightforward as pushing a button, energizing a coil. There's memory commands like this, like moves, which I actually use a lot. So what something like that would be used for is, say, pushing a signal to a display. So I have, let's see, I have rotary encoders that I'm controlling. And I want to know the position, and I want to output that position to a display. So what I'll do is you'll have one of these inputs that's basically just reading. It's an analog read. You're analog reading the counts. In that same rung, you can do math in that rung. So you can convert those counts to a angular position. You can do slope calculations. It's really, they make it pretty easy to do all this in a concise way in one rung. And then you can move, so you'll move that final position to the destination, which would be that display. So you can basically read, control, and output in one rung, which makes debugging super, super easy. So let's do an application real quick. First off, oh, there we go. I took this article from Coaster 101. This is a really great article in general. This is just a snapshot or a screenshot of a part that I'll paraphrase. But if you haven't read this already or haven't seen this already, I highly suggest you go and read it. So basically, this is just talking about the PLC application specifically for block systems. So I will summarize and paraphrase really quickly. Block systems, monitoring trains, and basically it's for safety. They don't want two trains to crash. As the main reason for controlling a roller coaster with a PLC is for safety, kind of like I mentioned earlier. So a design rule of thumb is you need one more block section than you have trains. And if you think about it, obviously that makes sense. You don't want two trains occupying the same or next to block sections at the same time. You always want a gap of space. So to detect the presence of trains, they will use proximity sensors or switches. Here they say proxy. I have never heard it called a proxy switch. I usually refer to them as prox switches, P-R-O-X. So in an example coming up, you will hear me say prox a lot. So it's basically just a proximity sensor. That is a very common, popular method used to detect the presence of roller coaster trains. So in here, it says there's a metal component attached to the underside of the train. So that specifically, that prox sensor would be called an inductive prox sensor because it's detecting the presence of metal. There's also capacitive prox sensors if you're trying to detect the presence of something non-metallic like plastic. These are non-contact sensors, by the way. So they're very robust because they don't get a lot of contact. You're supposed to never contact a prox sensor. So they have really small sensing ranges. The ones we use specifically can detect within a couple millimeters if you want to get that precise. So basically, a block system is comprised of a series of prox sensors that are detecting, or it's detecting trains and then counting the number of trains to make sure that basically the train is in a safe location to command the next train to do something. So with that in mind, we are going to do an example. So for background, we have just been contacted by by an amusement park to design a block system for one of their kiddie coasters. There's way too many millennials trying to get their coaster credits. They need to add another car. Basically, they want to improve their capacity of their kiddie coasters. So right now they have one car. What do we do? We're basically handed a clean slate. What do we want to do? So we can kind of think about the requirements. So they want to add one extra car. So they want 2 cars in total, which means we need 3 block sections. A good way to think of that is you'll want a block section in your station. You'll want a block section as an end brake, and you'll want a block section on your lift hill. This is a Kiddie coaster, so it's pretty small. There is no like mid brake section, but that is also a very common place for another block section. And in that case, you could have potentially 3 trains operating at one time. So the first thing to do when you are coming up with a control system like this is you want to define all your inputs and outputs. Funny enough, tomorrow when I go into work, I am designing a control system and I need to define my inputs and outputs. That's literally like my job tomorrow, is coming up with essentially this for a system that's controlling a big vacuum pump, basically. So for this example, our inputs are going to be the prox sensor for the end brake, the station, and the lift hill. So basically something that can detect the presence of a car at that section. And then you have outputs. So we will have, I tried to simplify it. It would be very hard to have a motor directly tied into a PLC. A good way you can do that is with a contactor. So you could have a motor tied into a contactor, and then with control, you could control that contactor switching on and off the motor. So for simplicity, I'm just going to call that motor. So you're going to have a motor for the lift hill, a motor for the station drive, and a motor for the end brake motor drive. And then you will have outputs for the brake, so something to actually engage the brake and lock the coaster in a safe position. So you'll have that at both the station and the end brake. So start off with a clean slate. You have a rung on the left, rung on the right. It looks familiar. We need the inputs on the left, outputs on the right. So the first thing, we'll go back to this if you want to get a picture. So we have the red car in the station is basically what we're getting from this. Red car in the station, blue train is somewhere on the track. So first step that we want to loop through is to detect the presence of a train in the end brake section. And when it detects that, to engage the brake and lock the train in a safe position. So ready for this insane animation, but we have the blue train traveling along the track. Whoa, hits the end brake. The prox sensor in that block section would detect that presence, lock the train. So now we have the blue train locked in the end brake section, red train is in the station. We can then use that end brake that we just energized as the input to the next command. So we can say if this is basically saying if the blue train is locked in a safe position, we can, I'm combining these into one thing. It's unlocking the brakes and then starting the drive motor for the station. So basically blue train is in a safe position, red train is being unlocked and starts driving toward the lift hill. Similarly, we can use that drive motor as the input, and we can start the motor for the lift hill. So as the train is moving toward the lift hill, we can start moving, or I'm sorry, oh yeah, I said that correctly. As the train is moving toward the lift hill, we can start the motor that would start turning the lift hill. So the red car moves up the lift hill. Somewhere on that lift hill, I would assume this is different for every coaster. This is something you would have to kind of define for the specific coaster, is where you want to put that prox switch. So you'd have to time it out of where is safe enough to be on the lift hill to be able to start moving the other train. So the prox sensor on the lift hill will detect the presence of the red train moving up, and then it will unlock the blue train and start driving it into the station for unloading. So blue train is now in the station. We need to detect that presence and lock it. And let's see. Okay. There we go. Okay, so blue train is now locked in the station. That's where you are unloading and then reloading while the red train is moving around the track. And then it basically loops back to the top. So this is continuously running. That's another thing about PLCs is that they're continuously running. So all of these could be in subroutines basically, where in the main you're calling each subroutine, and then you're constantly running these. So all of these inputs and all of these outputs would be basically consistently waiting for the next command, which kind of ties back to the repetitive nature of why you would use a PLC. It's a very specific, safe set of instructions that need monitoring. So now blue train is locked in the station, red train's moving around the track, and it loops back to waiting for the red train to hit the end brake section to start it all over. So that's basically how you would safely design a very basic control system. Obviously, it can and does get more complicated than that. It's not just a single proc sensor that's detecting that presence, because then you have to think about failure modes. For safety, I would definitely assume there's a series of proc sensors, and it's doing more than just detecting that presence. Like I said, it's counting individual trains. But the logic for that can get a little more confusing, so I thought this was a good example. So what now? Kind of ties back to the person who earlier said PLCs are expensive. And I thought this was funny. I saw in response to that, Robert in the chat said, Automation Direct PLCs have some good ones. You are right. You can buy your own, and I have Automation Direct PLCs linked in this presentation. So these are actually ones that we use at work. I really hope this link works.
Are those click PLCs?
They are click PLCs. Can you still see my screen, by the way? Okay, cool.
We're good.
So the click series PLCs are cheap enough. So let's see, $70. For $70 and a power supply, you can have a PLC as opposed to a 10 grand, 25 grand, whatever PLC. Obviously, they don't have the functionality that a Siemens or Allen Bradley would have, but we use them at work for controlling pretty basic applications. So just to kind of dip your toes in the water, this would be a really good thing to invest in. They have, it's very modular too. These click, it's kind of like how I was talking about earlier, where Allen Bradley has the remote chassis, but a lot of other ones have the plug and play on the side. This is one of them. So you can buy a whole bunch of analog and digital modules, plug into the side, and that's pretty much it. So for $70 and a power supply, which are about 25 to 30, so for $100, you can have a fully functioning PLC. There we go. So along with a PLC, you can buy hardware. This is the site that my company uses a lot for their hardware. In fact, I linked it right to inductive sensors. So if you wanted to, and I think this would be an incredible project to make an actual like scale control system for a roller coaster, you can buy proc sensors for, I mean, the ones we use are $25. So if you have 3 proc sensors and that full PLC setup, you're looking at under $200, and you could put together a really impressive project. Something I forgot to mention actually about the PLCs, those click PLCs, is it comes with free ladder logic software and pretty good documentation. So anyone can download it, anyone can test it out, anyone can program with it. I think both of these things would be a really cool thing for a club or a university group like yourselves to invest in. Maybe if you have club funding or something, that's something cool. It's also not expensive to the point where if you just personally want to own one, you could do that. So something else you could do is plan budgets. As an example, if you want as a group, as a club group for your school, if you put together like a small project of, okay, we want to design a control system. In theory, we're giving ourselves a budget of $20,000. Here's our inputs, here's our outputs. Can we actually make this happen under budget? So you can look up PLC distributors. So for instance, mine is Rexel is the company, but they distribute all of our Allen Bradley equipment. So you can email them, you can call them if you wanted to and get quotes. Even if you have no intention of buying them, they will send you quotes. And you can kind of see how much things cost, because the bad thing about PLC's equipment that's kind of more high end is they virtually never list prices anywhere. So you don't know how much something costs until you get a quote. And then what else can you do? Supplement some of this stuff for competitions. I know a lot of school groups do competitions. I think it would absolutely blow a judge out of the water if you designed a mock control system and put a budget together for a control system for like a dark ride or something. That would really put your project ahead of some other groups that maybe have good design or have good something like that. If you put together the work, even kind of how I did with just drawing it in Microsoft with the draw tools, I mean, it looks impressive enough, and I think it would really make your project stand out. So with that, thank you very much. That was really cool and fun to put together. Like I had way more fun putting that together than I would have thought, making all those animations. Because I'd never, obviously I do a lot of this PLC work at work, but it's never tailored specifically toward the themed entertainment industry, which I kind of have a passion for. So it's kind of fun to be able to apply this stuff to something I like. And just kind of as a side note, if you love this industry, but don't get into it right away, like that's very okay. I'm still learning a lot of very valuable skills that can still be applied to this industry at some point. My kind of goal in life is to work for Disney at some point, so I can kind of apply these skills to maybe something I want to do in the future. So I have some contact information there. If you want to send me an email about anything, go ahead. If you want to connect with me on LinkedIn, please do. And with that, I will take any and all questions.
Feel free to just go ahead and talk if you have a question there.
Oh, hi, Eric. This is Real. So I'm more of a software kind of guy, but just from listening, it sounds like I'd have to have more of a electrical and hardware background to be able to do this kind of thing.
That is not necessarily true. So another part of the programming side, there is ladder logic, but there's also a slightly more complicated way to program, which is basically just a scripting language. You can define all of your logic the same way you would in like a Python or a MATLAB or a C++. People usually don't do that because they find it easier to see the visual indicators of your rungs, but you can just as easily type out all the logic if you wanted. For the hardware specifically, yes, I would say it is more electrical oriented, but if you have an electrical engineer or an electrician lay this stuff out, it's good to know both the software and hardware, because as the programmer, you'll have to know which inputs all of your hardware is going into. So you'll basically have to understand the system, even if you don't understand the wiring necessarily.
Oh, that makes sense. Thank you.
Yep.
Eric, this is Robert. Awesome presentation. I'm glad that we were able to open this up to more people.
Oh yeah. Sure.
I'm kind of curious. I think you kind of briefly touched on this, but you talked a little bit about open. I think you said always open context versus always closed.
Sure.
So maybe I was wondering if you could. I've heard a little bit about those, but I was wondering if you could elaborate more and talk about maybe the applications in a roller coaster control panel of what would be always open or always closed.
Sure. So, normally open is basically just saying So, okay, say you have a proximity sensor. It's my finger. It honestly kind of looks like this. It's literally just a long piece of metal with an electromagnet here. It's a non-contact sensor. So we'll say this is a normally open proximity sensor. So when it's normally open, that means it will be, it won't energize until it detects this presence. So it's de-energized and a roller coaster train comes up, detects the presence, and now it closes. When that train leaves, it will jump back to open. So the opposite of that would be a normally closed proximity sensor. So right now, you're energized, even though there's nothing in the way of it. So now you have a roller coaster train comes through in the sensing range, and it cuts off that circuit. Different applications for those is kind of for safety. We have one normally open and one normally closed for some applications, and you're checking both, again, as just a redundancy of you want to really make sure that that pin is in the right place. So you have a normally open proximity sensor checking that, your pin is, let's see, it's normally open. Okay, if it's normally open, you want to check that your pin is engaged, and then you'll have a normally closed that also shifts and make sure that it shifted the right amount. So you could have some sort of offset that is basically double checking the safety of your system.
Awesome, thanks.
Yeah. That doesn't have to just do with prox sensors, by the way. Basically, any input you have could be a normally open or normally closed, like a limit switch or a push button. Any component you buy will pretty much specify if it's normally open or normally closed. And actually, in the program you write, it's a common practice to specify NO or NC. So someone who didn't actually write the program and is going to debug it or monitor it can see which contacts are normally open or normally closed.
Sweet. Any other questions out there?
How are more complicated like analog signals for something like, I don't know, direct torque control or anything that, it's not a one-to-one on-off? How are they handled in the ladder logic setup?
Right. So I haven't extensively used the Click PLCs, so I don't know if they have all the functionalities that some of the Allen Bradley stuff I've worked with does. But for Allen Bradley, I work a lot with analog signals. And a very common practice for an analog signal is a 4 to 20 signal. So that's 4 milliamps to 20 milliamps. And it does that as 4 being the low and 20 being the high. So with that remote chassis that I showed earlier, you can just plug in a card that's like a 4 to 20 analog input. So I have an input coming from a pressure transducer. I have this in a couple applications at work, so I'm more familiar with it. But you have an analog pressure transducer wired into this analog input card. In the program, you can read in that value in a rung. Basically, you'd still call it, it's interesting, you would still call it like an examine on. So even if though it's not like a Boolean, like an on-off, you read it in as an examine on, and it'll store that analog value that it's reading in memory and then can manipulate it later. So you're basically storing that value in the same line. You can manipulate that value, so you can add, multiply, subtract, divide, scale, anything, and then you can move it. So I think I mentioned earlier there was that move command. You can move that signal value to a destination. So in my example, I was moving an analog signal to a display. So that's a common application I actually use a couple places. So it's reading in that millivolt signal, storing that signal in memory, and then using that memory or manipulating that memory allocation basically, and kind of from there, if that makes sense. You can also do the same with an analog out. So if you have an analog output card you can write signals where you can generate the signals in memory, and then that card will generate the current signal as an analog signal to your output. So it's a little more complicated, but Allen Bradley makes it pretty easy with the hardware they give.
Cool. Thank you.
One question that I have is sort of, if you go back to the slide with like a top fill dragster control panel.
Sure. Yep.
Can you just sort of talk us through? I mean, like, I have never, been a ride op. Can you talk us through a little bit, like, what are all of these buttons for? Maybe not like every single one, but like, why are there so many buttons?
Okay, so I personally have also never been a ride op, so I don't know specifically for top thrill dragsters applications. I can talk about the one that I laid out, if that makes sense.
Well, that's perfect.
Okay. Take a sip of water for this. You never realize how dry your mouth gets after talking for 45 minutes until you actually do it. Okay. So this application, I actually didn't mention the application. I was supposed to. Whoops. This application it's basically lifting a very heavy hydraulically operated wall. So the wall to your right there, so it's, if you're the pilot's view left, so on the right side of the screen right now, that whole wall lifts up and then lifts down. And so that's how you can walk into the tunnel. That's also how you bring models in and out of the tunnel. So this panel is kind of like the control panel for that logic. So obviously it is a very heavy wall, so you need to have safety features in there. There's an emergency stop. So what that'll do is, it's a twist. I actually think in this picture, there was another control panel I was looking at for a roller coaster where it had literally this exact emergency stop. I thought that was cool. But it's a twist emergency stop, and it'll cut off exactly where it is. It's a variable frequency drive that is controlling the hydraulics. So it'll stay in the same place. It won't, like, if you cut off the power or anything, it won't drop down and smash it. It stays in a safe position. So that's if for some reason someone tries to crawl under the tunnel or under the wall for some reason. These are labeled. They're very small. Oh, I can zoom. So this is just an indicator for 24 volt. Okay, so that's just a visual feedback that the 24 volt power supply on the inside is okay and operating, it's on. And then the rest of these are all push buttons. So green, the one that's green right now is up. And these push buttons are pretty cool because they're a push button, but also there's an LED in them, and you can program the LED to do different things based on how you push the button. So right now in this application, this is indicating that the wall is all the way up and locked and in a safe position. If this green light was blinking, it's at the top, but it hasn't been locked yet. Like, it still needs to be locked. Down is off because obviously the wall is not down, but you can push that to move it down. What is that? Oh, there's your lock button. So I think I mentioned earlier those pins. That was an application for this. So there's 4 pins that's locking that wall safely into a safe position. So again, that green LED is just saying that the wall is locked in a safe position. What's next to it in red is unlock. So you can push that and it'll unlock those pins, which would then make this blink and make this blink. This is another layer of safety, basically. This is an enable and disable. So that's enabling and disabling your ability to control the wall. So if it's in enable, you can push all the buttons you want and it's not going to do anything. You have to switch off into enable to be able to basically move anything. So there's a write-up procedure on how to operate this wall. That is like the last thing you always do is disable control. So you know that anyone bumping by or bumping something in can't actually move this wall. You know what? These don't even work yet. These are for future applications. So these are going to be in auto up and auto down. So right now you have to hold that button in, and if you release it, the wall stops where it is. We eventually want to be able to just push that button, walk away, and have the wall do that whole sequence automatically without having to do the lock, the disable, all of that. So it's basically just adding future functionality. And then these two are, these are not push buttons, these are visual feedback again, but it's a little more complicated. There's a shaft, think like a clutch, and if the clutch is engaged, basically that'll light up, and if it's out, it'll stay off. And we need that to be off in order for the wall to go up. So it's basically just telling the operator, you need to look for that light before starting to move up. And it's a similar but different for this light. So a lot of it is there. Let's see, for push buttons right now, there's only like 4 push buttons, but there's a lot of visual feedback, which all ties back to the PLCs are very good for monitoring. So even without an HMI, which I've personally never programmed, but even without an HMI, there's a lot of good visual feedback here that can tell you what's safe and what's not safe. So I would imagine it's something similar for a roller coaster control panel. They look like very similar lights. I would imagine these have LEDs in them as well, probably telling you different things based on maybe where the train is on the track. I'm pretty sure someone said, and correct me if I'm wrong, I think Robert maybe even said for Top Thrill, the lights light up based on where the train is on the track at the right time. Is that right, Robert?
I can't confirm that, but from the labels, it looks like that probably is the case, and it's actually lined up. See the orange amber buttons are lined up like around in the shape of the loading unloading station. So if you think of it as like a U across from where the yellow, like over the yellow plated buttons, you can kind of see it's like the shape of the track. So yeah, I think each one of those is maybe a group of proximity sensors. But I don't quote me on that. We can reach out to Ryan Cash, who's operating Cedar Point from Ohio State too. We can verify for us. But yeah, that's my thought anyway.
Thank you, Robert.
Also, I just want to say this like panel on the right is, I think, nowadays overkill, because normally you'll have an HMI screen that'll just show you actively where your trains are. I don't remember when Top Thrill opened. I think maybe 2002 or something around this time. So I think at that time the Allen Bradley panel view screens weren't as, I guess, robust. So they opted for, I don't know how many buttons that is, amber buttons, to show blocks and positions of trains. So yeah, a little different than I think what they do nowadays.
Yep.
Awesome. Are there any other questions remaining?
Eric, I had one more question. I was kind of curious if you could talk a little bit about, you mentioned you'd love to work at Disney eventually. I would love to hear like kind of your story through college and how you came to figure out you wanted to do controls and like how you navigated, I guess, or considered working for the industry in college and what your internships taught you about your dreams, I guess.
Sure. So to preface, both of my parents are mechanical engineers. So I was kind of raised in an engineering household for the most part. So I came into Ohio State as an undeclared engineer. So basically that's just, you do all the core basic engineering courses, but you don't exactly know what discipline you want yet. So I think it was either first or second semester, sophomore year, Ohio State put on a presentation from, what was it? Lockheed Martin? I think it was Lockheed Martin. And they had an electrical engineer talk about the controls work she did on the B-2 stealth bomber project. And literally after coming out of that presentation, I'm like, this is the single coolest thing I've ever heard. And I need to be an electrical engineer right now. need to do controls, definitely want to work in the aerospace industry. So to that point, I kind of made it. Let's see. So yeah, I definitely had a focus of wanting to be in the aerospace field pretty early on. And I still really enjoy the aerospace field. I mean, I will probably stay here for a while. I've always, in general, just had a love of theme parks and amusement parks and roller coasters and dark rides and everything. I went to Disney quite a bit growing up. I went to my home park, Darien Lake, and Cedar Point a lot growing up. So I was always kind of around attractions and rides and thought they were super fun. I guess I never really considered it for a career path until I joined TPEG. The thing that kills me is I definitely remember seeing posters like all around my dorm freshman year for like join TPEG, and I'm like, wow, that sounds really cool. And then I just totally didn't. I didn't join TPEG until I was a junior, and that was like my first mistake for sure, because I only had 2 years in it and I had so much fun. And I definitely could have seen myself there longer. And I feel like if I had joined it earlier, I could very easily be in a different career path right now. I think that would have focused my career path even more, just so you could kind of do events like this and kind of see how of a cool, like a close-knit community this is. And there's networking. Like I don't think I've ever been to an aerospace engineering networking event. Like like who would put that on? This is so fun and cool. And I really just want to be more a part of this community in general. Why Disney as opposed to someone else is, if you can't tell, I kind of love Disney just by what's in the background. I've just always loved Disney anything. I love the storytelling aspect of rides in general. So that's why I would choose like a theme park over like a normal amusement park, or maybe a specific controls company. And then in summers, I had 3 internships. So my first one was at, it was called Jiffy Tight Manufacturing. So they made quick connects for fluid lines in cars, as exciting as that sounds. And one of the projects, like I literally showed up, this was between freshman and sophomore year. I showed up, and the first day they kind of looked at me and they're just like, so what can you do? And I was just like, I don't really know yet. I don't really know much. And one of the first things they said is, I see you're studying to be an electrical engineer. Can you do PLC programming? And I'm like, no, I have no idea what that is. And funny enough, in my next internship at, it was Mala Incorporated, they do automotive compressors. They also asked me if I knew how to do PLC programming, and I said no. So after two failed attempts, I kind of realized this is something important, and probably something that I should know if I'm expected to be an electrical engineer, and something I found that isn't wildly taught for some reason. I have found that it's taught more in like engineering technology programs, like the 2-year degrees, like the associate degrees, the more hands-on, not theory-based technical degrees. They do PLC classes, which honestly has probably a bigger application to what you would work on versus some of the theory that I learned and have since forgotten. So my third internship was at Calspan, where I'm still working. So after that internship, I guess I did a good enough job, and they invited me back, and here I am. So it really stemmed from, I mean, I guess the electrical engineer in general just stemmed from that presentation I went to, and the aerospace also stemmed from that presentation. So I guess what you can take away from that is I'm very easily influenced. And you know, I really do enjoy this industry. It's very interesting, and it's in a sense it has some, like, it sounds kind of impressive, which shouldn't be as important as I think it's kind of cool. But eventually, yes, I would absolutely love to work for a theme park company of some kind and kind of apply what I've learned over, or what I will continue to learn in the industry I'm in now to something else later that I might maybe enjoy more.
Awesome. Thank you for everything today, Eric. Let's give him a round of applause. Thank you for taking the time to talk with us and share your experiences. Do you mind sending me this PowerPoint
Yeah.
after this? And I'll share the PowerPoint, and then I'll pull the links out and share those links in specific as well with all of you who are on the call today.
Perfect.
With
Thank you.
that, just a reminder, we have a 3D printing session on Thursday, so come on out to that to learn from some fellow students on best practices regarding that. And if there's no other questions, feel free to go have a good rest of your night, and we'll see you later this week.
I was just Googling something real fast, and I was curious if you could answer this quickly.
Yep.
Do you know if PLCs can get race conditions, or if that's purely, if that happens, would that be a manufacturer error, or could you like code up a ladder logic thing that would get a race condition?
Is that race, R-A-C-E?
Yeah, race condition.
I do not know what a race condition is.
Oh, huh. Well,
Do you mean like when the signal's chasing itself, kind of in an infinite loop of sorts?
it's basically time-dependent behavior where if one of the things that's occurring, if at the end of its execution, it causes an error if it finishes before something else finishes, that kind of thing.
Got it. Okay. I think I would call that like a following error is how I've heard that. So you can set the, from Alan Bradley experience, you can set the clock rate of your PLC. So if you have an application that's running at a different speed than some of your other stuff, I would imagine you can change that clock rate to the slowest application so you don't have that following error.
Oh, okay. So then all of the signals apply simultaneously, whereas like in like traditional computer programming, one of them will happen first.
Right.
Whereas because it's clock based, then they all happen at the same time on the clock.
Right. Yes.
Oh, okay. Really cool.
Mm-hmm.
I can see why they prefer the PLCs then versus us doing the programming, like the traditional way.
Right. All right.
All right. Well, thank you for coming, Eric. It was a
Yeah,
blast
no
having
problem.
you join us.
Yeah, this was, like I said, this was really fun to put together.
I enjoyed those animations in the Kiddie coaster example.
It took me way longer than it should have to figure out, so thank you.
It was enjoyable. Feel free to come to any future those networking nights that we had. That you came to this most recent one.
Yeah.
Keep coming. I'll keep sending you the information each time they come up every other week. But we'd love to have you there. Give you
Awesome.
a chance to connect with more people.
Yeah, that was great. That was a great event.
Replace the lack of aerospace networking nights, I guess. So.
Yeah, there's a real hole in the theme park industry.
All right. Well, I'm gonna head out. Have a great day. I'll see you all around.
Thanks. You guys too.